Hi and welcome. In this tutorial, I'm going to discuss about the mechanical push buttons, how we can use them in our logic circuit or with microcontrollers. Here I have different type of push buttons. According to their size, I have large, medium and small push buttons. We can have 2 pins or 4 pins for a push button. If we have a 4-pin push button, then any of the 2 pins will be connected internally. When we are considering the working of a push button, then there will be 2 actions associated with a push button, which are press and release. We have to press the push button knob to get a signal out from the device, and when we will release the button, it will automatically come back to its initial position by means of some spring action or any other means. A push button can have 2 types, normally open and normally close. These 2 bubble points in this symbol represents the 2 pins of a push button, and this inverted T is the knob of the push button. In normally open push button, these 2 contacts will be in open position and there will be no direct connection between these 2 bubble points. And for normally closed push button, these 2 bubble points will be connected internally to a metal plate, which will make the contact from one end to another end, and we will get a direct path from one end to other end in normal position. We will provide the force to this normally open push button. It will make a contact between these 2 bubbles and provide a path for supply to flow. And for normally closed push button, if we apply the force, it will break a contact between these 2 bubbles and it will break the path for the supply. Now if I consider the circuit arrangement, how we can connect a push button for our logic circuit or for our microcontroller, then there are 2 configurations. The first one is known as pull down configuration and second one is known as pull up configuration. In pull down configuration, here we have a push button. One end of this push button is connected to a 5-volt power supply. This supply voltage will be equal to the supply voltage required for the logic circuit or microcontroller. The second pin of push button is connected to a resistance of value 10 kilo ohm and the other end of resistance is connected to ground. I have connected a DC voltmeter to check the output voltage from this circuit when we will press the button and we will release the button. And from this point we can connect this push button to our logic circuit or to a microcontroller. In pull down configuration, we will get normally logic 0 output when the push button is not pressed, and when we will press this button, it will give a high signal. On the other hand, in pull up configuration, one terminal of the push button is connected to ground and the other terminal is connected to this resistance of value 10 kilo ohm, and the resistance other end is connected to a VCC or supply voltage of required value. I have also connected a DC voltmeter here to check the status when we will press and release the button. From this point we will connect this push button to our logic circuit or to microcontroller. In pull-up configuration, we will get normally logic 1 or high signal at this point when this button is not pressed, and when we will press this button we will get a 0 signal. We know that the current will follow the least resistance path, and if we consider this open circuit as an infinite resistance, then this 10 kilo ohm resistance will be a negligible resistance and this supply voltage will not come to this point when this push button is open, and our logic circuit will get this path and this path through the resistance towards the ground. Hence, on the normal position when the push button is not pressed, we will get output 0 or logic 0. When we will press this push button, now this will act as a short circuit, and now here the resistance will be negligible as compared to this resistance of 10 kilo ohm, and now the current from this supply source will follow this path towards this side, and our logic circuit will get a high signal. I can run the simulation for these 2 circuits in the Proteus ISIS. You can see when this switch is not pressed on the DC voltmeter, I am getting this 0.00 volt, which is normally logic 0. And for this pull-up configuration, on this voltmeter I am getting plus 5 volt or the voltage equal to this VCC, and this is normally logic 1 when the push button is not pressed. Now if I press this button, I will get positive 5 volt or the voltage equal to VCC, and when I press this push button in pull-up configuration, I will get 0 volt or ground signal. We want sharp rising and sharp falling edges when we will press and release the push button. This ideal waveform is very hard to achieve because when we will press the push button, we will encounter this problem, which is also known as bouncing effect. Before getting a perfect signal output from the push button, we will get multiple bouncing waves because of the mechanical contacts making and breaking. And these multiple signals can lead us to a false detection of the button press and release. To get rid of the bounce effect from mechanical push buttons, the simplest arrangement is to use the 100 nanofarad capacitor across a push button. The capacitors will smooth out the wave output from the push button and we will get nearly ideal signal from the circuit. So I have two options. While dealing with the push buttons for my electronic circuits, I can either use this pull down configuration or pull up configuration. I will discuss the use of these two configurations in other video tutorials. For now, just focus on these two concepts. Thanks for watching the video and don't forget to subscribe the channel.